Hi, this is Jonathan Gardner. This is example 10 from section 722 of Griffith's Introduction to Electrodynamics, second edition. The example here is we have a very long solenoid, infinite length, because it's very long. We're just going to assume it's infinite. And it goes out, and I probably made it too small. Okay, and so this has, wires wrapped around it all the way down the middle. And then inside of this guy, we have a little cutaway here. We have another solenoid. Okay, this one on the inside. Let me just draw a couple more wires here. Okay, this one on the inside has a radius of r. Let me use a different color here. So this is r. And it has N1 turns per unit length. And this one over here has N2 turns per unit length. The radius of the one on the outside doesn't matter. Because, anyway, you'll see. So the idea is that we want to calculate that if we put a current through the small one, what is the magnetic flux through the big one? And the solution is that the field generated by this small one is actually really complicated. And I don't want to solve that integral. But what I do know is that the mutual inductance of the current flowing through here, calculated the phi of this guy, is the same as if I calculated the current flowing through here and calculated the phi of that guy. Well, this guy is going to generate a uniform magnetic field, and then we can calculate the flux rather easily that way. So I'm going to work backwards and then flip it around for the front ways. Okay, so the magnetic field generated by the outer loop, by the outer solenoid, is drawn on previous equations, mu naught, the number of turns per unit length, times the current flowing through it. Okay. So the flux through a single loop of the guy on the inside there is just b pi r squared. And so that gives us mu naught into I pi r squared. Sorry about my handwriting. Now, how many loops are there? Well, there's N1 loops on the inside guy per unit length. Length L and N1 loops, which is N1L loops on the inside. So we have N1L b pi r squared is the total flux through there, equals mu naught N2 I pi r squared N1L. And so this is the total flux phi. Okay, and it equals all that stuff on the right side. So let's try to break it out. So we have mu naught pi r squared, and we have N1 and N2 and the length, and then the current. Okay, so this bit right here is the mutual inductance M. Okay, and so now that we know the mutual inductance M, we know that if a current flows through the inside guy, it's going to generate a flux of whatever the current is on the inside guy times M. Okay, that's because we just shown that the mutual inductance, it doesn't matter which way you're calculating, backwards or forwards, it's going to be the same. So cool, that was actually rather easy. So sometimes when you have a problem like this, you can work backwards, just like Newton's third law. If you have a force pushing in one way and it's hard to calculate, why don't you try calculating the force that's pushing back against it? That might be easier. So thanks for your time. Bye.